Hello everyone, and welcome to this presentation in which the next 10 minutes are going to be dedicated to ThermalSynth, a novel approach for generating synthetic thermal human scenarios. My name is Mia, and I am an industrial PhD student at the Danish company Milestone Systems. I am here today on behalf of my colleague Nilu and all remaining co-authors of this paper from our Visual Analysis and Perception Lab at Aalborg University here in Denmark in order to present the work that we managed to accomplish together. So with our project, we contribute with 4 key achievements. First of all, we propose a novel approach to generate synthetic thermal datasets, and we apply that data generation approach to one particular use case in which we would like to detect human falls into water. At the same time, we show domain adaptation from synthetic to a real dataset for human fall detection. And we do this by means of 2 standard classification networks, out of which the first one is AlexNet and the second one ResNet 18. And last but not least, we are proud to report state-of-the-art results on a real-world dataset for human fall detection. Now you might all ask yourselves, why would we want to do something like this? So let me convince you with the following motivation. According to a report from the World Health Organization on global drowning prevention, at least 236,000 people die every year because of drowning, and drowning is one of the 10 leading causes of death for people aged between 1 and 24 years. Now, this is a pretty alarming thing, and we as engineers might right now ask ourselves how we could solve this kind of problem, right? Or at least provide a computer vision solution to reduce the amount of fatalities as much as we possibly can with a possibly deep learning solution. Now, if we would like to design such a system, probably the most important question we have to ask ourselves is, how do we collect enough data to train a deep learning model in the very first place, right? We cannot just ask people to voluntarily jump into the water, or can we? Well, in fact, there is a work that has been published earlier that is doing exactly that. The authors of the paper to the left have asked a bunch of volunteers to jump into the water at the harbor front, which is like this entire scene has been recorded by a thermal camera that is mounted at the harbor front in Aalborg University, close to one of the faculties. And you can see that the people are voluntarily jumping into the water. At the same time, there has been work going on where a mannequin has been prepared in such a way that it would resemble a human in the best possible way, and then mannequin has been thrown multiple times by one of the researchers to the harbor front in order to model these kind of scenarios. Now you can imagine that neither of these approaches leads us to a data set that would have a sufficient amount of images that we could train our models on. So what our team decided to do was to design a new dataset generation process, which can be split into 4 main steps. Firstly, there's the background extraction. Secondly, there's a synthetic foreground preparation going on. Then we fuse our real backgrounds together with our synthetic foregrounds. And then last but not least, there's the task of fall detection, which we would like to accomplish with the resulting dataset. When it comes to the background extraction step, this is most probably the easiest step in this entire pipeline, because all we do is apply a temporal mean filter on all the videos that we have at hand in order to remove the moving objects from the scene to be able to retain the background frames only. Now coming to the most interesting part of this work, we modeled the synthetic foreground generation process in the following way. We decided to choose several different Mixamo characters from the Mixamo platform and chose them in the full animations in order to have the most realistic result achieved. And since those characters come in RGB, we had to implement a thermal shader in order to be able to blend them into our thermal background scene. This thermal shader is based on the Stefan Boltzmann law and a few post-processing steps which allow us to mimic the quality of, say, almost every thermal camera out there that is just mounted in the wild and suffering some artifacts. So we apply Gaussian blur, some noise, discrete cosine transform to obtain the level that you can see on this slide. We fuse the synthetic foregrounds with our real backgrounds by modeling the background in Unity at first to specify where our static objects are located. Then we place our foreground objects into our region of interest. We extract 3 consecutive frames from our full animation and encode those 3 frames in one RGB image, which is representing the temporal dimension, such as the spatial dimension at the same time, and this is the input to both of our networks. These networks, as I have already mentioned before, are AlexNet and ResNet 18, and we perform domain adaptation by training these 2 data sets solely on our synthetic images that we generated, and then by testing on the real and semi-real data from which you have seen the 2 videos earlier in this presentation. So when we look at the performance, we can see that AlexNet is reaching an astonishing accuracy of 98.7% when it comes to full classification capabilities. This refers to the real data sets that we tested on. When it comes to semi-real data sets, then the accuracy is dropping a little bit, but one could argue that it's still sufficiently high to see this as a promising approach to perform fall detection. And ResNet is performing equally well, one could say, on a global scale when comparing these 2 networks to each other. It is also very important to notice the high specificity and sensitivity values that we reach here. To conclude our work, we can definitely say that ThermalSynth is applicable to any kind of use case, so you do not need to focus on humans that are falling into the water only. You can model but basically any kind of situation that you are capable of modeling, in game engines such as Unity, for instance, or Unreal for that matter. We do not have any privacy concerns whatsoever because we are operating in the thermal image domain. But of course, one disadvantage of our fall detection approach is that we are assuming an ideal scenario where there is no other objects in the water that could possibly occlude our object of interest. And this leads us to the future work that we would like to work with, which would be the inclusion of more objects into our scene. We also would like to enhance our thermal shader a little bit, and at the same time, the ultimate goal is to extend this classification task to also perform anomaly detection. So thank you very much for your attention, for your interest, and if you have any questions, please don't hesitate to reach out.